morning. Last time I was talking about transmission electron microscopy and we were just talking electron microscopy principle and that was discussed that depending upon the characteristics right of the primary beam which may have the 400 kilo electron volt of energy and may start from 50 kilo electron volt. So, a high beam of energy and the electrons just impinge on the surface right and then it can be primary, secondary or back scattered electron and energy of these electrons which may diffract, which may transmit from the surface is measured right. So, electron which have wavelength of roughly approximately 1 angstrom. So, that energy can be calculated and based on that one can determine the surface morphology right. So, that was discussed. So, transmission electron microscopy as I said that something which transmits. So, if it is a pore, so electron will transmit through the pore. If it is a hard surface, so it may not right. So, that will come as a black spot. So, this is what the dark spot on the positive of the detecting film that correspond to the dense area. So, suppose there is a platinum then it will show black, but if it is alumina the metal will or electron will transfer through the pores of that right. So, the dark spot from the outline of the metal particles or crystalline right crystallites. So, that can be used to find out the composition right. This can be used to find out the morphology, topology like SAM right, but TEM gives you 2D plane. So, over a mass of the solid, total mass of the solid. So, generally as we talked that the electron beam of high energy electron beam right that is depending on the properties of the material is examined right. The properties include density, composition. So, based on this density of the solid and composition, structural composition. So, metal part is there, support is there, different metal may be there. So, the electronic configuration is different. So, depending upon that you can distinguish between the metals right. So, porous material suppose you have. So, it will allow more electron to pass through while dense material will allow less. So, you can distinguish right. So, based on this the non-uniform density can be examined. So, uniformity of the surface or chemical composition of the surface can be traced by using this transmission electron microscopy. So, we were talking about this picture right. So, as I said how a surface is created. So, this you can just if you look at here the copper zinc oxide catalyst and the treatment or conditions are here it is treated with hydrogen, here it is in the environment of water and hydrogen and in third case it is with carbon monoxide. So, you can see that when the treatment gases are different then the surface which has created on the support is changed, that morphology has been changed right. This you can very easily say here the depth you can see here this and then here it appears to be centered one right the agglomerated. So, how a surface is created that is again a different theory that the free energy of the surface is measured right and when the metal is interacting with the support. So, free energy depending upon the faces or planes right and the center of that crystal. So, the energy is calculated right and that is known as surface free energy. So, Wolf construction that is one of the important method to determine the shape of a crystal or how does a crystal forms, because as I said it depends on the energy. So, d orbitals if you look at transition metals which have unpaired d electron they have highest energy right and they will try to dissipate it, because when the surface is created the energy you have to provide certain kind of energy right. A large molecule it is to be ruptured. So, energy is increasing for the at the end for the given molecule right. So, this principle is used here. So, when you use the transmission electron micrograph then you see the structures like this depending upon the electron energy on different phases right. So, this you can very easily if you look at the structure here which has shown here the different planes HCP structures, hexagonal closed packed body centered cubic. So, face centered cubic there can be different kind of structure of a crystal plane right lattice plane. So, 1 1 1 0 0 1, but I was talking earlier during X-ray diffraction pattern you observe them, because the diffraction at different diffractions and different positions right the X-ray which emits and their wavelength is, that is lambda is known. So, you can calculate the from different planes, right, what is the crystal or phase and what is the orientation of that crystal, because when the reaction takes place, the orientation of that metal on a support is also important. So, this is what I am talking here is the orientation of these planes, right. So, there are different structure here 110 plane, then 100 plane, 110, this is 111, right. Body. So, different orientations of a lattice when you see, so x y z plane and how these are arranged in that plane, right, how an atom has been arranged in a plane. So, that structure can be identified. So, when you have a time plane, so you can see here that this is one kind of, this is your zinc oxide like this, you can see a boundary here. So, zinc oxide. So, you can measure the crystal size of zinc oxide also, right, by just looking this distance, because this distance is 2 nanometer. So, what is this distance? So, roughly here the copper particle size is 0.21 nanometer, right, and if this is copper 200, it has a crystal size of roughly 0.18 nanometer. So, in this case if you see, it is 0.21 nanometer, in this case again it is 0.21 nanometer. So, size has increased if you look at compare from this and this, right. This is because of the agglomeration. So, one can get the idea if you have a transmission electron micrograph. So, you can get the structure or you can get the idea about the composition of the metal. So, this is what the inference from this, the shape and morphology of the copper particle that vary dynamically and reversibly with the gas composition. So, depending upon the gas composition it is changing, right, because it is a chemically reactive gas which have been gases which have been sent, right. So, depending upon the adsorption or chemisorption strong or weaker. So, there can be a change in the surface structure. So, such changes in morphology are driven by the interface energy. So, that is what related to the Wolf construction, right, and can be used to determine the structure, because the gamma is proportional to the distance, right. Surface energy, if the structure, if I just say that is forming something like this, if you have a structure like this. So, we are measuring distance from this, right, distance this, distance this, right. So, this is what, if I am saying this is h I, this is say h j, this is say h k. So, energy, surface energy gamma is proportional to distance of this, right, h I or h j or h k. So, if this distance is high, so you are larger. So, it means the gamma k will be larger than this one and then this one. So, then you can have that how this surface is forming. So, depending upon this distances, the surface energy is different of each plane. So, this plane, this plane, this plane and so on, so on. So, you can get the idea about the crystal geometry, right. So, crystal geometry plays a very important role during catalytic activity. So, that is what the nano particles, when you are saying its shape is changing basically, right. So, as I discussed here also that under hydrogen or a mixture of water and hydrogen, the copper particles tend to form faceted half spheres, right, while the particles spread over zinc surface in the carbon monoxide containing atmosphere. So, the gas environment also change the structure of the metal, right, it can change the structure of the metal, right. So, this is again another picture just which shows that this is a nickel particle, basically the catalyst which have been used here is nickel silica, right, nickel on silica support, and then the methane decomposition reaction has been carried out. So, after reaction also you can get that what structure has been formed, right. So, this is your nickel particle and you can see that it is not spherical in shape, right. So, the shape of the nickel, so nickel particle is here because it is dense. So, you are looking at a black, and this is nothing but the carbon which is deposited on the nickel. So, nickel, on the nickel the carbon is growing in the form of fiber, right. So, that is another interpretation which you can get from the transmission electron spectroscopy that or microscopy, what surface or what type of carbon material has been formed after the reaction, right, on a metal, or how does it grow on the surface of a metal. So, topology and the morphology or structural composition of the catalyst before and after the reaction can be compared by using transmission electron microscopy. This is another picture. If you have high resolution transmission electron microscopy, right, at high energy. So, you can check the structure of the carbon which has been deposited on the catalyst, right. So, you can see here that it is a kind of nanotubes, right, and it can be just that if you just look at the closure picture, there are different layers of the carbon inside, right. So, that can give you the idea about that if you have one A type catalyst, B type catalyst. So, you can get the idea about their ID, OD, right. So, this is the internal diameter of the carbon nanotube and this is the outer diameter of the carbon nanotube. So, one can predict that there are two layers, right, or it can be a multi-walled carbon nanotube, right, if you go further analysis of this graphitic structure of the carbon. So, one can get the idea about these kind of structural changes, the morphology of the carbon formed during the reaction or similar other observation from transmission electron microscopy. This is another example where the copper cobalt catalyst has been used for Fischer-Tropsch reaction. So, by looking if you just go through that and then take a closure picture at higher magnification. So, this is your copper particle, these are your cobalt particles. So, copper has come in between the cobalt particle if you look at, right, and then one can interpret that the dispersion is high or low. If the cobalt particles are together, they may agglomerate during reaction, right, which may not be good for the Fischer-Tropsch reaction. But if you have the promoter copper which is acting here as a promoter, so small concentration of copper may enhance that dispersion. So, one can interpret that why dispersion of cobalt increased in the addition of in the presence of copper on the catalyst, right. So, these kind of analysis can be provided by doing this transmission electron micrograph. Similarly, scanning electron micrograph, right. So, here again the fundamental things are same, that is again we are using the electron beam, right, but these are secondary kind of electrons or back scattered electron or it can be X-ray also. So, this can be associated with X-ray diffraction also. So, we call it EDX, energy dispersive X-ray analysis, right. So, here again sequential imaging which is similar to optical scanning confocal microscope. So, just like in your optical microscope you take a picture. So, it is just a picture of that surface, right, but using the electron not the light source, photons or other low energy sources. So, this can be used in reflection or transmission mode. So, whatever the different approaches can be used here. So, the principle wise if you look at the scanning electron microscopy involves mastering a narrow electron beam over the surface and detecting the yield of secondary or back scattered electron as a function of the position of the primary beam. So, it may be a diffracted beam, right, depending upon the orientation of the metal on the catalyst and the beam which strikes on that, right. So, depending upon that it may be diffract, right. So, the diffraction energy can be measured, it can be back scattered. So, the energy of these secondary beams or back scattered electrons can be measured, right. The part of the surface facing the detector appear brighter than the part of the surface with their surface normal pointing away from the detector. So, you will have something like a bright image in the case of scanning electron micrograph, right, because it is a diffracted from the surface of the metal. The secondary electrons roughly they have the energy between 5 and 50 electron volt, right, and these originate from the surface region of the sample. So, once we measure the energy, this is same fundamental thing is same, that we are measuring the energy of these beams, right, the kinetic energy of the beam and then correlating because different metals have different property and depending upon their property or electronic configuration, the energy of this refracted beam will change, right. So, back scattered electron generally they come from a deeper and carry information on the composition of the sample, right, because heavy elements are more efficient scatters and appear brighter in the image. So, again when you have the beam electron beam, so the diffraction or it comes from a secondary or the lower layer of the atom, right. So, back scattered electron, secondary electron, what you have seen in the case of X phase also, right. So, the electrons are here used, right, rather than the photons. So, XPS like XPS or like your TEM, The SEM can also be used for determining the composition, right, but the TEM gives you whole mass of the sample 2D image, right. You will not get here that kind of image in the scanning electron. So, because it is just like a pictorial diagram, microscopic view of that surface, right. So, the composition, crystal structure, orientation, these can be obtained, and these are based on, as I said, electron backscatter diffraction, EDX, energy dispersive X-ray analysis, which can give you the composition of the surface, right. Only the point wise at different points you can determine the surface composition, and then you can just take the average. So, it can give you the overall composition on the surface of the metal if you have at different locations, right. Otherwise, it can be localized also, and this may not be correct result if you use SEM EDX for determining the chemical composition, right. And Auger electron emission, because again these are the secondary and backscattered electrons, so Auger electrons, right. So, you can have the information regarding the Auger electrons also. So, in EDX, as I said, this SEM EDX can be connected together, and because X-ray sources which come from this surface, that their energy, and they can look at the diffraction from the surface, right, at different wavelength. So, the diffraction pattern, which is spots from single crystal particles, can be used to identify the crystallographic phases in XRD, right. So, just like your X-ray plane. So, here you can use this information for determining the chemical composition. In XRD you just get the phases, right. So, the emitted X-rays are characteristic of an element and allow for determination of chemical composition of a selected part of the sample. So, that is the difference, because the intensity, light intensity which you have in X-ray, the wavelength is fixed, right. When you do the X-ray diffraction, you use a copper potassium alpha radiation, say 1.5 angstrom. Here the wavelength can also be varied, right. So, in that energy dispersive X-ray. This is just a picture that you have a source of energy beam, electron gun, right, and there are condenser lens to get the monochromatic energy, right, monoenergetic beam, and then the scan coil which pass through the objective lens. So, sample is placed here, right. In TEM you place sample somewhere here, but sample is placed here. So, the diffraction comes. So, which may be, if it is X-ray, then X-ray detector like EDX, electron detector. So, you measure the energy of these electrons, and then information can be transmitted in terms of the phase composition, structural composition, right, particle size, morphology. So, whether particle is spherical in shape or irregular, right, cylindrical in shape. So, all these kind of information, agglomeration of the particle after reaction. So, these information can be obtained from SEM. If you do SEM EDX, then you can find out what is the percentage of potassium in your catalyst, what is the percentage of sodium or any other metal also, right. But as I said, it is a point or line analysis, right, not for the whole surface. You cannot take just from one set of data. So, at one point the composition may be very high, but at the other point it may be 0, right. So, then there may be error. So, this is just a comparison among all these methods, that but SEM, TEM and optical microscope. So, this is just an optical microscope, right. You have a light source, right, where you have a condenser lens, and then you have a specimen sample placed here, then objective beam, and you have a eyepiece here. So, you can look at the property of the sample, right, which can be transferred to a computer, and you just take the data, right. It just picture, if your particle is larger in size, it can do, right, with certain magnification 50 times, 100 times, right, something like that. So, just like a microscope, but here you use the electron beams, whether it is TEM or SEM, right. So, this is your TEM, transmission electron micrograph, and this is your SEM, right. So, your sample in TEM is placed here, right. So, this is the sample specimen, right, and in this case the sample is placed here, transmission, and other things, if you look at, you have a lens here, right, and another lens here also, right. You have a beam deflector here, because you are looking at deflection patterns of these, right. So, this is sent to here and then diffracted or X-ray beams, and then you have just the detector, right, when then image on viewing screen. So, you can look at the composition of the particle, and that can be a different magnification. So, in SEM or TEM you can go up to a magnification of 10 to the 5 or 10 to the 6 also, right. In the TEM also you had the same thing, specimen. So, then this is a projector here, right, and then you have the image on fluorescent screen. So, that can be viewed and you can get the composition or surface analysis. Anatomy, the structure wise is again, so electron gun, right, the source may be cathode rays or right different type of beams, anode, right, condenser lens, the condenser lens 1, condenser lens 2 to get the monochromatic beam, energy beam, and then you have a variable aperture here. This is connected to vacuum. So, vacuum is very high, right, 10 of minus 5 to 10 of minus 5 to 10 of minus 6 millibar, right, very low vacuum. And this is the specimen which is placed here. So, diffraction takes place and these are the measured diffraction cells to measure that. So, secondary electron beam detector, condenser lens 3, whatever the diffraction transmission from here. So, you can measure the different properties of the secondary electron, back scattered electron, right, or X-ray. So, energy of these or intensity can be measured and that can be correlated for the surface composition. So, this is just what kind of information you get on the same catalyst nickel, earlier the transmission electron micrograph. So, this is the scanning electron micrograph picture, right. So, these are the nickel particles brighter spot, and this growth which has taken place like this is your carbon fiber, right, carbon nanotube which grow on the metal surface, right. So, white spot is your nickel, because as I said here you get a brighter image, in TEM it was a darker image, right. So, then the growth or this diameter can be find out, particle size can be find out. So, these information can be obtained from scanning electron micrographs. So, similarly, this you can see the different catalysts and they can compare their structure. So, as it is mentioned here that irregular shape particles here, you cannot see any definite shape here. So, these are the irregular shape particles, right, of the catalyst. The second one is something like elongated, in lengthwise it has increased like this. So, elongated shape particles, right, which is average particle size of 150 micron. Third one is again irregular admixture of small and large particles. So, there are some particles which are small in size, but there are other particles which are larger in size. So, one can interpret these information from the scanning electron micrograph, right. When you do EDX, then you can have the composition also. So, like oxygen, zinc, sodium, silicon, like this, lead, potassium. So, this is just for a ceramic material, like red particles which have been shown here, the EDX spectra of the particle, right. So, one can, and this black outline, these are just for the normal ceramic material, this is right. So, by doing this SEM EDX, you can distinguish from the original material or original support and the when the metal has been impregnated, and you can compare what changes have occurred on the surface when that metal have been loaded or a composition of the different metals have been loaded. So, a comparison can be made, but as I said that this will be just a point analysis or a line analysis, it cannot be taken considered for the whole surface, right. You have to do this at different points or different positions and then take the average. The another characterization is based on ion technique, right, and the important one is the secondary ion mass spectrometry, right. So, the first this one we were talking so far same term based on electron guns, right. Earlier we were talking about photons or X-rays, right, beams. So, this is another one and has become one of the most important or important tool for characterization of the catalyst, right. Again it can talk about the oxidation states also, just like Mossbauer spectroscopy, right. So, this was first developed by NASA in 1960 just to analyze the composition of the moon rock, right. So, the composition may be different silicates, calcium, aluminates, so this kind of composition. So, later on this has been just used or developed for the catalyst also. So, secondary ion mass spectroscopy, as the word says secondary ions, right, not the primary ions. So, which have just from the lower surface of the atom, right, the ions which have come from the lower. So, it is used to determine the composition of organic and inorganic solids at the outer 5 nanometer of a sample, right. So, that depth is roughly of the order of 50 angstrom, right, 5 nanometer. This can generate a spatial or depth profile of element or molecular concentration. So, information can be obtained for a catalyst, right, up to a certain depth, and the profiles can be used to generate element specific image of the sample that display the varying concentration over the area of the sample. So, at different locations you can find out the compositions, right, or the oxidation states of the catalyst or whatever the surface which is formed or created during the preparation, right. So, the impurities can be determined, right. So, semiconductors and thin filaments, if you have materials like that, then you can find out the impurity also, right. So, principle is more or less same, that instead of the electron beam you have some ion source, right, which is primary ions, they just strike on the sample and then you have some secondary ions, right, like just like back scattered ions and or diffracted ions, and then they are taken to an energy analyzer and which is connected to a mass spectrometer, right, and mass spectrometer is connected to the detector, and then you can have the spectrum of those compounds, right, the ions which have been irradiated from the surface of a solid or catalyst, right. So, you can see the depth profile also, you can see the image also. So, all these informations can be used from this, right. So, generation of the secondary ion, that is the first thing, right. So, sample is prepared in an ultra high vacuum, right, very high vacuum is required for the process. The beam of primary ions or neutral particles, they impact on the surface with energy 3 to 20 kilo electron volt. So, roughly the primary ions have the energy of order or from vary from the 3 to 20 kilo electron volt. So, primary ion particle cause collision cascade among a surface atom, and between 0.1 and 10 atoms are usually ejected. Roughly 10% of the atoms are ejected from the surface, or which are the secondary ions, right, because it depends on the type of the surface, it depends on the energy of the primary ion, and then these are kind of back scattered ions which comes from the first top layers, right. So, first, second, third layers of the atoms, right, and the process is known as sputtering, right. The sputter yield depends on the nature of the sample. So, depending upon the nature of the sample, you have the different kind of secondary ions, and once you measure their energy or their intensity, then you can correlate it with the surface or the metal. This is just a picture of collision cascade. So, primary ion, so this is the surface over layer of surface, and these are the atoms. So, when it strikes, so they collide among themselves, right. So, this is what the kind of collision, right, and then you get secondary ions because of the collision among these atoms, right, and then these atoms leave the surface. So, negative electron and then this positive. So, these secondary ions and these energy which comes from the primary ion, because of the primary ion which strikes on the surface and collide. So, they come out and the energy is measured. So, this is what the target atom. So, up to this 5 nanometer depth one can measure the information on the surface or metal, right. So, of these ejected atoms, some are ionized, which are roughly less than 10% as I said, and these are known as secondary ions, right. So, the energy which is or the energy of these ions which are roughly not more than 10%, right. The matrix of the sample must be known to accurately determine elemental concentration. So, you should know some prior information about the metal, because that you know based on your preparation what metal has been taken, what salts have been taken, right, for the preparation of the catalyst. So, these are known based on, because it is a kind of dictionary from where you have to shortlist, right, which component, just like you do in your GCMS also, right, gas chromatography, mass spectrometry or any other chromatography. So, you should have some prior information about the sample, and this can, because once you know that, so you can get the idea about the elemental concentration, as ionization yield can vary as much as 3 orders of magnitude between nearly identical atomic sputtering field, because that is what the very crucial, that you have to differentiate, you should be able to differentiate between the closure atoms or closure ions which come out, because once if you have two very close atoms, the property of the secondary ion will also be similar, right. Then you should be able to distinguish them, right. Same thing in the any analysis, when you have a just like in X-ray also I told you that JCPDS is generally one of the package which is used, but there also the D values will be very closer. You have to just ensure and you have to be very careful when you identify. Same thing in GCMS also and same thing here also, right. So, secondary ions can be analyzed by using the mass spectroscopy. There can be different type of SIMS. So, static SIMS, imaging SIMS or dynamic SIMS. So, imaging, as the name says, that basically this imaging will give you the picture just like an MRI image, right. So, picture it talks about the picture of that structure of the surface, right. It takes the image, but static SIMS, this is used to determine the surface concentration of elements and molecules without significantly altering the sample, right. So, you can get the composition by using this method, static SIMS. So, most of the time we use this for the catalytic purpose, right. Imaging SIMS like static SIMS does not alter the sample too much. This mode is used to generate images or maps of the samples based upon concentration of one secondary ion representing either an element or molecule. So, it takes the image of that surface, rather talking in terms of peak which you get in the form of concentration, it will image that just like your transmission electron micrograph, right. So, you can look at the composition or you can get the idea about the morphology or topology of the surface, right. But dynamic SIMS involves the use of much higher energy primary beam, which is a larger ampere beam current, and it is used to generate sample depth profiles. So, if you need in depth analysis, then the dynamic secondary ion mass spectroscopy method is used. Most of the time the static SIMS is used to determine the concentration or composition of the surface. So, in the static SIMS low ion flux is used, right. So, what does it mean? That small amount of primary ions is used to bombard the sample per area per unit time, right. That is what called ion flux, right. The bombard the sample per unit area per unit time is known as ion flux. Sputter away approximately only 1/10 of an atomic monolayer, right. So, the depth will be small here in this case, right. So, 1/10 of an atomic monolayer information can be obtained when you have this kind of ion flux, low ion flux, right. So, organ, xenon, argon in terms of the form of their ions, or organ and xenon are the commonly used particles, they are present in the primary particle beam and which has the diameter of roughly 2 to 3 millimeter, right. So, these kind of sources are used for this ion mass spectroscopy. The analysis typically requires more than 15 minutes. So, not too much time is taken here, and technique generates mass spectra data well suited for detection of organic molecules, right. So, this is just the information which I am providing, that what methods can be used for characterization of a surface, right. So, I am not going in depth analysis of these methods, or I am not going in chemistry or physics of the atoms or the instrument. So, imaging is again another method, as I told, by using SIMS. So, mass spectrometer here is set only to detect one mass. The particle beam traces a raster pattern over the sample with low ion flux beam, right, as in SIMS, and typical beam particles here, it consists of gallium or indium ion, and the beam diameter is approximately 100 nanometer here. So, you can take the image with that, right, of the order of 100 nanometer, and again time taken is just 15 minutes or even less than 15 minutes. The intensity of signal detected for particular mass is plotted against the location that generated in this by this signal, right. So, basically again just like in transmission electron micrograph, you take the image, or scanning electron micrograph. So, here the images are generated rather than the concentration. So, intensity of the signal detected for a particular mass is plotted. So, it is based on mass to mass basis, right. So, particular mass is very important here, that we are talking mass to mass basis, right, is plotted against the location that is generated this signal, right. So, that is correlated with that, and absolute quantity is difficult to measure, right, but for a relatively homogeneous sample the relative concentration differences are measurable and evident on an image. So, one can differentiate between the two surfaces very easily, right. With one surface you cannot get the idea about the composition just from the image, right. So, if you have two say before reaction, after reaction, or catalyst A with A type of composition and catalyst B with different composition with slight modification. So, you can have the image just like in your transmission electron micrograph you have seen, right, but this one can give you some in depth analysis also, right, unlike in a transmission micrograph. So, this is just a picture for static SIMS, right. So, in static SIMS you get the just at different mass, atomic mass units, right, and versus the intensity. So, one can just like in gas chromatography and mass spectrometry, one can correlate these with their corresponding say positive ions or either the negative also. So, this is for positive and this is for negative, and same compound polymethylene methacrylate SIMS, right. So, structure can be determined by understanding these, because at different mass, right, you are getting the composition which may not be visible right now, but this is just like O negative here. This is your CH negative, this is your CH3O negative. Here if you look at here, this is your CH3 plus. So, one can correlate this positive and negative, like, and then can correlate it with the composition. So, this is just a one chemical composition, and same thing can be done when you have a catalyst material. So, these kind of peak can be correlated with the composition of the matter, right. And when you look at image, you can get the image something like this. So, this is just for a quartz material feldspar. So, you can see the image like this, white spots, right, like this. So, you can compare for sodium this, silicon this, potassium this, and this will come appear at different for a particular, say I told mass unit, right. So, at different locations you have this kind, and that is related to the mass of that sample, right. So, that these images can be correlated when you have A and B. So, I can very easily distinguish between sodium and potassium, because they will appear at different mass, right. So, one can get this information which is similar to your transmission electron micrograph, but here the it can be in depth also, right. So, you can get the idea about the composition of the or surface structure or morphology of the surface and in depth, right, up to certain depth. Same thing for dynamic also. When you have dynamic SIMS, the higher flux ion is used compared to the static, right, or image SIMS, right. So, here it is high flux, and this eats away at the surface of the sample, burying the beam steadily deeper into the sample and generating secondary ions that characterize the composition at varying depths. So, this is much more appropriate or much more in depth analysis, right, but you need a high energy beam for this kind. So, here the beam typically consists of oxygen plus or cesium plus ions, right, which has a diameter of less than 10 micron, right. So, these are related to the diameter of these primary beam ions, right. The earlier case it was of the order of millimeter, nanometer like that, right. So, different beam diameters. So, and then you can get the analysis of the surface. So, the experiment time here it is less than a second. So, very quick response you get from this dynamic method, right. And ion yield change with time as primary particles build up on the sample, affecting the ejection and path of the secondary ions, right. So, this can be used to get the complete composition of the surface, right. So, I am not going in details of these, but these methods can be used for characterization of the sample. So, this is what the response you get in terms of the depth in micrometers here 0.2, 0.4. So, this is just the depth profile of hydrogen embedded in silicon. So, you can get the information in terms of the at what depth the hydrogen has penetrated on the surface, right. So, just like in chemisorption you get. So, once you have done chemisorption you can do this and then you can get the idea about the metal support interaction also, right. So, that these information can be useful when you look at your hydrogen spill over on the catalyst or the metal support interaction, when we say the strong metal support interaction and the different gases. So, information can be obtained. So, this is just the hydrogen concentration on the it is a function of depth of the surface of a solid, right. So, dynamic SIMS can be used for this purpose. The another characterization technique is known as Mossbauer spectroscopy, right, MS. So, this can give you the oxidation state, but only for the selected metals which have magnetic property, right. So, for iron if it is on a catalyst, then this is more prominent or more effective method, right. So, this provides the oxidation state, the internal magnetic field and lattice symmetry of limited number of elements. So, this can be these elements can be like iron, cobalt, tin, iridium, ruthenium, antimony, platinum and gold, right. So, that is it means you need to prepare the catalyst with some radioactive source element, right. So, very selected metals, but the analysis is more accurate when you have the Mossbauer spectroscopy for this kind, right. The effect is described as a recoil free emission and resonant absorption of gamma radiation by the nuclei, right. So, these are kind of the neutral what we say the methods, right, where you can have the IR spectroscopy is one where you look at the vibrational energy in right and you can characterize the catalyst using the bonding or between the metal support after reaction the composition can be analyzed, right. Same thing here in Mossbauer for the magnetized material it can be determined. So, the principle is something like this, that we measure this gamma energy, right, energy of the that is what the recoil what you call. So, you have free emitting and absorbing atoms, right. So, emits radiation and absorbs it, right. So, this is what the recoil we call the recoil is that is based on this Mossbauer spectroscopy based on this principle, right. So, that will not happen for all kind of metal, right. It will happen only for the radioactive metals or which have the magnetic property. So, energy of recoil can be calculated and correlated with the gamma ray energy and m is the mass of the atom. So, this energy of recoil or gamma energy is function of this mass of the atom. So, different metals will have different mass atomic mass. So, this can be correlated with the property of that metal. So, this is what when there is no recoil, right. So, that is what your no recoil here. So, you will not get any kind of diffraction or any kind of intensity variation. So, it will not have any gamma radiation in one way. So, Mossbauer spectroscopy is the recoil free emission, right, and absorption of the gamma rays. So, that is the Mossbauer spectroscopy. So, just quickly I will show you that what kind of structures you can get here, that you can compare, because it is a kind of shift now, right, in terms of energy shift what you call when some absorption is taking place. So, depending upon the local environments just for iron atoms of the iron atom and the magnetic properties, the Mossbauer spectra of iron oxide can consist of singlet, a doublet or a sextet, right. So, it depends on the atomic mass, right, and the magnetic property of the metal, right, because the coil what I said recoil, that analysis or gamma energy that generated will be principle of the property of the metal or the atomic mass of that metal. So, the symmetric charge with no magnetic field. So, there is negligible shift, right, no shift in energy. So, you will have just one peak here, right, and when asymmetric charge with no magnetic field, again there is a splitting, right, but the effect is not measured. But in the case of when the asymmetric charge and magnetic field, then you have internal and external. So, you get 6 peak here something like this. So, one can compare the oxidation states of the iron which is present on the catalyst by using this. So, this is just correlated here again in this form Fa3 plus So, if you just relative transmission versus velocity, so you have the shift in that. So, this shift is related to the property of the atom. So, oxidation state of the matter atom. So, iron 2, iron 3. So, these can be distinguished, which is shown here like this, right. So, iron 2 has a shift like this, iron 3 has this. So, you can measure that shift at different velocity. So, it is a kind of fingerprinting also, because once you know the oxidation state, you can just talk about these different oxidation states here like this Fe2 plus, Fe3 plus, right, and which is just in terms of isomer shift or velocity, right. So, that is the energy shift what we talk when you have a kind of radiation, right. So, it is when for a radioactive material, we are just calculating that for different radioactive material depending upon their gamma energy, right, and related with the energy of the source, right, the Mossbauer what we are talking in this equation. So, just this equation which we are talking here, right. So, these two recoil energy and this surface energy or the gamma radiation is function of mass. So, depending upon these two, you will have different kind of shift here in terms of energy shift, and that shift is related to the oxidation state of these metals. So, that is what, and once you know those information, then you can just look at in terms of the splitting of these, right, atoms or the mass. So, isomer shifts and quadruple splitting of iron bearing phases vary systematically as a function of oxidation state, right, the metal oxidation state, metal spin. So, iron spin states and iron coordination, right. So, how these are coordinated. So, knowledge of the Mossbauer spectra parameters or can therefore be used to fingerprint an unknown phase. So, you can identify the phases by using this Mossbauer spectroscopy, but only thing that it is true only for magnetic materials like iron, right, but not for all kind of metals. So, for selected metal, but this provides a very useful information, right, but TEM may not be effective, but this can be effective. The another which is based on neutral technique is atomic emission spectroscopy. So, IR spectroscopy, all of you know, ultraviolet UV spectrophotometer, you know, right, it can be used to determine the composition, chemical composition, right. So, and can provide you the total concentration of the metal inside the catalyst. So, once you extract the metal from the catalyst and then you do the UV at a particular wavelength, and then you can find out the total concentration by measuring the absorbance as a function of concentration, calibrate it and you can find out total concentration, right. IR spectroscopy can give you the chemical composition once, right, after reaction or absorption. So, you can just talk at different wave numbers, right, and then see the absorption. So, you can identify the composition, right. So, IR, FTIR, the chemical bonding can be used by using Fourier transform infrared spectroscopy. So, before reaction, after reaction, and you can have the structure or composition, right. But there are some other technique like atomic absorption spectroscopy, ICP, inductive coupled plasma, right. These are based on neutral technique and they are versatile in terms of determining the total concentration of the solid catalyst, right, that is metal concentration in the final catalyst, because initial loading is one thing, you have done the calcination, you have done the reduction, and based on those calcination reduction, then finally after that you need to find out the final composition, because during the heat treatment there may be a loss of the metal, active metal. So, in that case it becomes important that you correlate the catalytic property or your turnover number dispersion which you define based on this actual composition of the metal on the catalyst. So, that is important. So, in that case this atomic absorption, right, which is the absorption of light by free atoms. So, here we are not talking any ions, we are not talking any electron, right, not talking any photon or X-ray, right, neutral technique, right. So, neutral atom in the gaseous state can absorb radiation and transfer an electron to an excited state, right, that will depend on the type of metal, right. So, you need a different type of lamps to measure their absorption, because they will be for a particular wavelength, right, absorption will be. So, an atomic absorption spectrometer, if you just look at, is an instrument that use this principle to analyze the concentration of metals in solution, which is very important for the catalyst, when you prepare the catalyst, the final concentration of the metal is to be determined. So, this can be used, which is known as AAS also, atomic absorption spectrometer, right. The substance in a solution are suctioned into an excited phase, where they undergo vaporization and are broken down into small fragmented atoms by discharge, flame or plasma. So, there can be a flame. So, flame detector, right, flame ionization method. There can be a plasma method, which requires very high temperature. So, depending upon the type, you can determine the absorption. So, the ions will generate, right, or the metal comes in the ionic state and you measure the concentration of those ions. It can come in the vapor state, gas phase, you measure the concentration, right. So, in UV it is just in the solution and you are making some complex and which comes at a particular absorbance wavelength, right, particular wavelength, and then you correlate it with the original concentration. So, there can be, you need to do certain kind of initial calibration or titration in order to confirm them. So, by exposing these atoms to such temperature that they are able to jump to high energy levels and in return they emit light. So, what happens when you have given this kind of, right, the some high voltage or high a furnace, right, a high temperature furnace which is used, a graphite furnace can be used, right, or plasma. So, under these conditions, these are broken down, all the solutions suctioned in the excited phase, where they undergo, right, vaporization and broken down into small fragmented atoms by discharge, flame or plasma, and these atoms, right, at such a high temperature they just able to jump, right, and reach to a higher energy level, right, and in return they just emit light, right. And the versatility of atomic absorption, which is an analytical technique, instrumental method, right, has led to the development of commercial instruments. So, this is one of the important tool in terms of characterization of the catalyst and also other just in other inorganic chemistry, just to find out the composition of the metals, right, purity of the metals, all these things can be done by using this. Yes. So, whatever the light emitted, that is measured by that definite lamp. So, a specific lamp is required when you have atomic absorption spectrometer, right. So, more than 68 metals can be analyzed by that, right, the important tool. So, this is just a simple, if you look at the principle is very simple, you have some excitation source, right, and so once you have that, this you get excited atoms which is connected, which is passed through some lamps, right, and you have a lamp here which is a definite wavelength selector, right, you have to select that wavelength for absorption of that particular metal, right, because a particular metal will emit the light at a particular wavelength and which can be absorbed. So, that is here, right, and you pass through a detector and you get the concentration, because the absorbance versus concentration can be calibrated, and for any unknown sample, once you know its absorbance, you can correlate it with the concentration, and database are available nowadays. So, that there can be the different types of high temperature plasmas, right. So, one is the inductive coupled plasma. So, this is widely used method for the characterization, right. Principle is what we have talked or discussed, right. Then second one is a direct current plasma, then microwave induced plasma, and most important of these is what the ICP method, right. So, sometimes ICP AES also, atomic emission spectrometer, right. So, there can be a variety to get the complete composition of the metal. So, ICP is a tool by which you can find out the composition of the catalyst, complete composition, right, which may not be correct from the SEM EDX, right, but this is a much more versatile compared to SEM EDX. So, direct current plasma technique. So, just principle I am talking, not in detail. So, you have the direct current plasma and which is created by the electronic release of the two electrodes. So, very high voltage electrodes, right, are used. The samples are placed on an electrode. In the technique, the solid samples are placed near the discharge to encourage the emission of the sample by converted gas atom, right. So, very versatile technique. So, you have just the electrode here, right, and you have a solid sample here. So, discharge between the electrode sputtered sample atom and that pass through the detector and you absorb that, measure the absorbance. So, is related to the concentration of that metal. ICP AES, right, as I said, inductive coupled plasma also is connected with atomic emission spectra, right. So, inductively coupled plasmas are at least 2 times as hot as the flames or furnace. So, very high temperature is generally used, as I mentioned here, that common plasma temperatures are 6000 to 10,000 Kelvin, very high temperature, right. So, atomic absorption you use the graphite furnace, right, you use the acetylene lamp, acetylene flame, right, burn the using the acetylene and then generate that temperature, right. So, you need a cylinder to burn that and generate the temperature of that order. So, you need a high temperature, right. So, graphite furnace may be required when you have very high temperature of the order of 1200 degree centigrade. So, the organ plasma is the result of the flow of organ ions in a very strong localized radio field, right. So, these kind of lamps are required generally, right, and hot enough to excite most electrons, so that they can emit the light, right. So, they are hot enough to prevent the formation of most interferences, break down oxides and eliminate most molecular spectral interference. So, this is a versatile technique in that way that it can determine you the actual composition of the metal, right. So, with this I just close this characterization part. So, next time I will cover the zeolite, right. Thank you.